a particle is it's an irreducible representation of the Poincaré group. But I'm afraid most people wouldn't know what this means.
Welcome, everyone. So, at the heart of physics is the search for ultimate particles. The Standard Model sets out the current framework, but many argue that all is not well in the particle physics zoo. A central prediction was the existence of supersymmetry particles, but none have been found. At the same time, huge experiments have failed to find particles that account for dark matter and dark energy, which make up 95% of the universe. Moreover, it's not even clear what a particle even is, since some have no dimension and others have no mass. Yet physics is rife with proposals for new particles. While there are positive spin-offs from the technology created to carry out particle experiments, has the theory itself run out of road? Would we be better describing reality as the product of quantum fields, information, or mathematics rather than particles? Or does the Standard Model not actually describe the ultimate nature of reality at all? And do its particles just represent a useful fiction? We have a fantastic panel for you today. Sabine Hossenfelder is a theoretical physicist who specializes in the foundations of physics. She's the author of Existential Physics, a scientist's guide to life's biggest questions. Gavin Salam is Oxford-based theoretical physicist, celebrated for his groundbreaking work in quantum chromodynamics, the theory describing strong nuclear force. And Bjørn Ekeberg is a philosopher of science and the author of Metaphysical Experiments, Physics and the Invention of the Universe. So welcome to my panel. So we're all gathered here today to ask and debate a central question, which is, are we right to continue searching for ultimate particles in the way we have done for the past 50 years? And I'm going to put that to Sabine first.
Oh, I get to go first. All right. So I think my answer to the question is no. Okay, so I guess I should expand a little. So for the past 50 years, we've had good reasons to think that we haven't yet found all the fundamental particles of nature. So we've had this thing called the Standard Model, and we have had certain theoretical expectations of what should be in that model, what kind of particles, how many of them, what should their properties be. And over the course of time, we've filled in the model. So we found them all. The last particle to be found was the Higgs boson, which was found at the Large Hadron Collider in 2012. And with that, the Standard Model of particle physics is complete. Now, theoretical physicists have some misgivings about that Standard Model. They basically think it's not pretty enough. And this is why they've proposed that there should be other particles, because then it would be prettier. I don't think that's a particularly good motivation to keep on looking for new particles. And so I think at this moment in time, particle physics is in a good shape. You know, it works well. The Standard Model describes all our observations in particle physics. But we have other things to worry about, notably in astrophysics, where we have these things, dark matter, dark energy. There's some things we don't understand about the expansion of the universe. We have some issues with quantum mechanics and so on. So those are all areas where we are doing and should be doing experiments to push the boundaries, to learn more about the foundations of physics. But at this particular moment in time, I think investing more into particle physics is not the right thing to do.
Thank you, Sabine. Gavin, I'm going to go to you next.
Okay. So Sabine and I are sitting at opposite ends of this panel, unsurprisingly, because we have opposite views. A good sort of two swords length between us. So unsurprisingly, I'm going to say I think we should carry on. I think the only way we have of understanding and probing and exploring whether there are new particles is by building colliders and running those colliders. But perhaps where I really disagree with Sabine is her statement that the Standard Model is complete. There's two aspects to particle physics. There's the particles, and the set of particles is complete. And there's the interactions. And the interactions are nowhere near complete. In fact, one of the mysteries of the Standard Model of particle physics is that all around us there's a field. Fields, that's physics talk. What is a field? Well, a magnetic field is something everyone knows about. You've got a compass, you can sort of detect that magnetic field. And we know what causes that magnetic field. It's because there's a big magnet in the middle of the Earth. Well, all around us there's another field. It's the Higgs field. And that Higgs field has a much, much bigger impact on us than the magnetic field of the Earth. Or rather, the Standard Model says it does. But there's not a shred of evidence for why the field has the value that the Standard Model says it does. And there's not a shred of evidence for it actually having the impact on us that the Standard Model says it does. For example, it gives the electron its mass. Now, electron mass is 0.05% of our mass. You might think, who cares about that? But 0.05% of mass actually sets the size of atoms. And if it were half of that mass, if the electron mass were different, we'd be twice our size. And supposedly that comes because the electron interacts with the Higgs field. That's a hypothesis. It's not been tested. And so there are a whole set of questions out there that particle physics actually could answer in the next 70 or 100 years. We're thinking big time scales. It's not easy. But we think that particle physics could get there and actually would really shed light on the world around us or definitively rule out the Standard Model.
Thank you, Gavin. Bjørn?
Well, if we put this a little bit in history, you alluded to in the beginning, we have 50 years of particle physics. We actually have about 100, 120 years of what we could call atomism, which is the forerunner of the particle physics that we have. The idea of the atom, or this idea that there is an indivisible particle, something that came up early in the 1900s, and nobody believed in it before, until it happened and it changed the whole discourse, changed the whole field of physics as well. I mentioned this at the outset because this idea that there is, the smaller the constituent you find is the ultimate constituent, the ultimate particle, as we talk about. This is part of the narrative, I would even say maybe the illusion of atomism that is brought along, that if we just keep finding smaller and smaller bits and pieces, we would find then the ultimate story. The history of particle physics is really a history of experimentation with high energy physics colliders generating more, as we would think of it, more insight into finding new particles. But these particles are experimental phenomena. They emerge every time we build a bigger collider, we increase the probability of finding more subatomic particles, parts of them. This is why a lot of people in the field would like to have built something even more to go further, to expand and potentially find more particles. But this idea might turn out to be a bit misguided. Maybe this is what I would suggest, is instead of searching for smaller and smaller constituents, maybe what is lacking in theoretical physics and the Standard Model right now is a better understanding of how things actually hang together, not what the ultimate smallest pieces are.
Okay, so I'm getting a distinction between knowing about particles and knowing about fields, but Sabine, do we actually know what particles are? Have we got that established, in your opinion?
Well, I'd say particle physicists know pretty well what particles are. I mean, they have that going for them. Though I have to say, I read the description of this debate and I came across the question, what is a particle? And I have to admit that when I would have to answer this question, I'd say, well, a particle it's an irreducible representation of the Poincare group. But I'm afraid most people wouldn't know what this means or what to do with it. So I think that the way that I think about those questions, what is this or what is that, is what's the mathematics that we use to describe this thing? And we understand this very well. So we use certain types of mathematical operators in certain types of spaces. Then we have this thing that we call quantum field theory, and it's really complicated with all kinds of operators and so on. And we have that part down. And so I'm not sure that science can even answer the question beyond that. Like, what could possibly answer the question? What a particle is beyond this mathematical construct that we use to describe it. I don't know.
So then does the standard model represent reality then?
It describes it. Does it represent it? I don't know. It's the best we can do.
Gavin, what's your view?
I'm actually pretty much on the same wavelength as Sabine here.
Oh. You can move your chairs together.
At the end of the day, you've got a description and you've got data. You can go and do an experiment and collect data. And you ask, do they agree, do they not agree? And if they agree, you're doing a good job. Now you can try and ask about the philosophy that's behind the description, and sometimes you can get your head pretty tangled up. But if that tangle doesn't predict anything different about what the data is going to look like, that tangle at some level is metaphysical rather than scientific. And so far, it predicts everything extremely well. So there's not really an issue there.
So Bjørn, what are we talking about then on this stage if everyone's in agreement?
Well, I think it's important to have the distinction between perhaps a particle, which we tend to, in the broader sense of the term, we tend to think of that as indivisible units. And then there's particle concepts. I mean, you could take this as far as saying there is no such thing. If you're going to take the lessons of particle physics for the last 50 years, you could say, what it has shown is that ultimately there are no particles. When you break things down, there are dynamic structures, there's virtual particles, quasi-particles, there's interactions, fields that you don't find. The deeper into nature you probe at the levels of resolution, or with the higher energies you probe, you find that there is nothing that is indivisible there. The whole premise for particle physics was that it was a search for those ultimate units, right? But particle concepts are necessary to physics practice. So we have many particle concepts. They are necessary for an experiment to run. And there's a fundamental circularity here in the history of particle physics, is that in order to run an experiment, you do need to formulate a particle concept. In order to find that particle, you have to run an experiment. That's why I want to bring this up to the discussion, because it's so closely tied to the experimental practice, to large experiments, to colliders and so on, because particles are literally produced or generated from this experimental practice. So maybe it's just important to keep in mind that what physicists talk about as particles, as Sabine says, particle physicists know really well what particles are for the practical use for physicists. The important thing then for these physicists is that they can use those concepts to generate more research and more particles and so on. That doesn't necessarily translate into what most people would think of as particles, as actual units in nature.
So are we continuing the search for ultimate particles, or are we done? We found everything there is to find?
Well, it's always dangerous to say you're done. Historically, when people thought they were done, they probed further and they found actually they weren't done at all. For example, they found that protons and neutrons had stuff inside them. They had a size. They had constituents. You never really know the answer to that question, and that's part of where the difficulty and the disagreement maybe is. Because when do you stop? If you don't know if you're done, when do you stop? Do you always just carry on going further and further and further? And if you find nothing, and you carry on finding nothing, and you carry on finding nothing, do you stop? And that question of finding nothing is, in a sense, one of the elements of where we disagree, because we haven't found any new particles since the Higgs boson was discovered. But we have found interactions that we'd never looked at before. And I would say we're actually finding stuff, and we've made major discoveries over the past 5 years, and there's major discoveries still to come. So in that sense, there's definitely a future. There's definitely something that you can target, that you can hope to reach, as opposed to the ultimate particle where you don't know what the target is, you don't know if you'll reach it.
So is that what we're discussing then? That we have found a particle like the Higgs boson. We haven't found anything of significance since. And so are we at some kind of fork in the road in our approach?
Well, it's a little unfair, I think, to say we haven't found anything of significance since the Higgs boson. Yeah, so first of all, let me say that I agree with what Gavin said, that we never know that we're done. And I didn't mean to raise the impression that we're sure there's nothing more. Of course, we don't know. It might be that there are more particles. For example, we have the stuff that we call dark matter that we don't really know what it's made of. And a lot of physicists think that it's actually made of particles, which raises the question, well, how could we find out? So you can try to produce those particles, for which you could use a really big particle collider, or you can try to measure the ones that go through our planet, and there are experiments running that have been looking for those since the 1980s. The problem is they haven't found any. And this raises the question, like, how long are you going to continue with this kind of thing until you give up? And I've come to the conclusion that this just isn't a particularly useful strategy to keep poking around in the dark, building detectors, hoping that the kind of particle that you believe exists turns up in this detector. It's just not working. And when it comes to building bigger colliders, it's true, of course. You build a bigger collider, you can make more precise measurements. You can learn things that are interesting for particle physicists, like properties about the Higgs field, how it interacts with fermions, whatever. And it's true, there are things that we haven't measured before, and I'm not saying they're uninteresting, but it's not like we make a fundamental breakthrough by measuring those things. And this is why I think that at this present moment, there are just better things that we could be doing in the foundations of physics. And so particle physics at this point in time is not a particularly hot research area.
Gavin, what do you say to that?
So one of the dangers in science is having a blind spot. And I think there's a problem that the field has a blind spot, which is this assumption that just because you've looked at the standard model over and over again, and it seems to have worked, that the whole of the thing is right. And the bit we've looked at is the bit that's like electromagnetism. Basically, the standard model has electromagnetism in all sorts of variants, and we've tested that bit over and over again. But the whole thing rests on a completely different structure. And that other structure, which is connected to the Higgs, actually, we're only just barely starting to probe. So it's pretty fundamental. In fact, it's arguably it's the keystone of the whole standard model. So to say that we don't need to look at it just because things have worked so far, I think is really sort of a dereliction of duty for a physicist. It also ties in many ways with fundamental questions, like dark energy. We don't know. The universe is expanding faster and faster, but only very, very slightly. And when you look at the standard model, without really adjusting it very finely, you'd have a completely different properties of the universe. And they're connected with this Higgs field. And what we cannot do is actually figure out whether the Higgs field is what is driving this or not, or how it's connected with that. But when you know that there's a problem, that you're basically almost a brutal inconsistency in your theory, then you better go and check that theory in more detail. And that's the attitude that I take with respect to this.
So Bjørn, as someone sitting in between these two perspectives, should we carry on as we have been doing?
So I find it's not my role to be prescriptive about what we should be doing with physics, because I'm an interloper in the sense I'm not a physicist, I'm not vested to any of that development. But I find it interesting that what we talk about here as the potential dead end theoretically, or have we reached end of the road for a theory, is really tied to an experimental limit. Like we have built the biggest collider we have so far that found the Higgs boson, which was actually theorized in the 70s. The question of whether we can move further is really tied to the question of should we build another particle accelerator, should we build an experiment that has the potential to go further. If you look at it historically, there's always the indication that when you build something at higher energies, you can observe more, you could find more, you could generate more research. I take this whole debate and the climate between these two speakers also as indicative of maybe some of the deeper underlying curiosity and motivation to find the fundamental building blocks of nature and so on. Maybe it's dissipated somewhat in the last decades or two, that it's not moving any further because there doesn't seem to be any new accelerator on the horizon or a collider on the horizon that could answer new questions. So it's tied to like being at the limit, basically, of what we can know, I think, at the current stage.
Sabine, would building new accelerators be worth the cost?
Well, I don't think so, but before I make my point, maybe I should clarify, it's not that I think, or I don't think anyone in physics thinks that the standard model is the last word. We do have good reasons to think that there's more than the standard model. Like, for example, there's some issues with the neutrinos. There are issues with the quantization of gravity. There are issues, at least I would say, with the measurement problem in quantum mechanics and so on. It's just that building bigger colliders isn't going to do anything about those issues. And also dark energy, I don't think you'd learn anything from a bigger collider about dark energy unless you get very, very, very lucky. It's possible, but I find it very unlikely because it's really a cosmological thing. And yes, there are some ideas that it has something to do with the Higgs boson, but it's not generally accepted thing. And this is why I think if we want to make headway on those problems that we want to know an answer to, like what is dark matter, what is dark energy, what's with the measurement problem, quantum gravity and so on, there are better experiments that we could do. So I think that the smart thing to do at this time is to invest the money into those experiments where we have a fair chance to actually find something new, and that would help the theory development. And then we can try to decide, like, is it now worth building a bigger collider to test some of these things? Like, for example, you might be looking out into the cosmos and actually figure out where dark matter has to be made of some kind of particle which has this and that energy and this and that interaction. And then we know what's the kind of detector or the kind of machine to build to investigate that kind of thing. But at the moment, we're not in that position.